In this video, I will discuss the increasing trend of the successive ionization's energy of an element and also how we can use the successive ionization's energy data to determine group, period, and also plot of an element. Hey, I'm Teacher Tan. If you like my videos, do remember to click on the subscribe button below so that you won't miss any notifications as I update my channel. Now we move on to look at successive ionization's energies of element. In this table, there are three elements: sodium, magnesium, and aluminium. Can you see that for each of these elements, the successive ionization's energy values increases? Why? Successive ionization's energies of an element increase because as electrons continuously be removed, the number of protons in the element is still the same. Hence, the effective nuclear charge in the species increases, and therefore the attractions of the nucleus on the remaining electrons become stronger. As the attractions of nucleus on the remaining electrons become stronger, this means that the distance between the nucleus and the remaining electrons become closer, and more energy therefore is required to remove the next electron. Why do we want to know successive ionization's energies of an element? From the successive ionization's energies of an element, basically we can get a few informations regarding on the element. The first informations that we can obtain is the number of valence electrons that particular element have. From the number of valence electron, we can write the electronic configurations of the element and determine the group and also the plot of the element. The second information that we can get is the number of shells filled with electrons. By knowing the number of shells filled with electrons for a particular element, then we can identify the period of the element in the periodic table. From the successive ionization's energies values, how could we determine how many number of valence electrons and how many number of shells filled with electrons does an element have? In order for us to determine this, first we need to plot a graph. We need to plot the graph of ionization's energy versus the number of electron removed, or we can plot the graph of lot ionization's energy values versus the number of electron removed. From the graph then, we can identify where is the drastic increase. Like for example, in the graph here, the drastic increase is when the second electron is being removed. Hence, we can say that the drastic increase occurs between IE1 and IE2. From the drastic increase, we can deduce that the second electron started to be removed from the inner shell of the element. From the graph, we can also see that between second to the ninth electrons, the increase in ionization's energy is at a constant rate. Hence, we can say that the second to the ninth electrons, they are in the same inner shell. From the 9th to the 10th electrons, again we see a drastic increase. So this means that the 10th electron is being removed from another inner shell. Between the 10th and the 11th electrons, once again the variations in ionization's energy is almost constant, and therefore we can conclude that the 10th to the 11th electrons, they are in the same inner shell. From the deductions that we made just now, could you tell me which one is the outermost shell? Why? Must remember that outermost shell refers to the shell that is furthest away from the nucleus. Hence, if the electron is in the outermost shell, the electron would require less amount of energy to be removed. By knowing which one is the outermost shell, we then can deduce how many electrons are there in the outermost shell, or how many valence electrons does the element have. Previously, we have deduced that the drastic increase occurs between first and the second ionization's energy. From the drastic increase, we can conclude that started from the second electrons, the electrons are being removed from the inner shell. This also implies that the electron before the second electron is removed from the outermost shell. And from the graph, we can conclude that there is only one electron in the outermost shell of this element. From the graph, we can also determine that this element consists of how many shells filled with electrons. From the graph, we can see that this element consists of 3 shells filled with electrons: the outermost shells, inner shell, and the innermost shell. So 3 shells filled with electrons. That's why the highest principal quantum number is equal to 3, and this element therefore is located in the period 3 in the periodic table. From all the deductions that we make, now we can come to the conclusions. The first conclusions that we can make is this element consists of 1 valence electron, and there are 3 shells filled with electrons. Therefore, the valence electronic configurations for this element is 3s1, and the electronic configurations of the element is 1s2, 2s2, 2p6, 3s1, and this element is the s block element and group 1 element. If we are being given a full set of successive ionization energy data of an element, then we can deduce the group, period, and blot of the element in the periodic table. But sometimes we are not being given the full set of data. If we are not being given the full set of successive ionization energies of an element, we can still do some deductions. We can still determine the number of valence electron, write the valence electronic configuration, determine the group and also the blot of the element. For this, instead of plotting a graph, we just need to calculate the ratio. So how to calculate the ratio? Basically, we use the next ionization energy value divide with the previous ionization energy value. For example, to calculate the ratio, we use the second ionization energy 1817 divided by the first ionization energy value 578 to give us the ratio 3.14. We do the same ratio calculations for third ionization energy and second ionization energy, and the same calculations repeated for the fourth ionization energy and the third ionization energy. After the ratio is obtained, then we need to look for the biggest ratio value. Like for example, in this element, the biggest ratio is between the third ionization energy to the fourth ionization energy. From this highest ratio value, we then can identify the drastic increase. The largest ratio value indicates where is the drastic increase. The largest ratio value we calculated was between third ionization energy to the fourth ionization energy. Hence, the drastic increase occurs between the third ionization energy to the fourth ionization energy. From the drastic increase, we can deduce that the fourth electron is removed from the inner shell, which is closer to the nucleus and has more stable electronic configuration. Hence, we need more energy to remove this fourth electron from the element L. From this drastic increase, we can also deduce how many valence electrons does element L have. We can also write the valence electronic configurations of element L and also determine the group and also blot for the element L. As drastic increase occurs between third ionization energy to the fourth ionization energy, we can conclude that started from the fourth electrons are being removed from the inner shells. Hence, 3 electrons before the fourth electrons are being removed from the outermost shell, and therefore element L has 3 valence electrons, and the valence electronic configuration is ns2 np1. We use n here because we do not know how many shells filled with electrons does element L have? From the valence electronic configurations, we can conclude that element L is in p block and in group 13 in the periodic table. One more thing you need to take note is, for successive ionization's energy, we can only deduce the elements in S block and P block.